Today we're going to talk about rotational equilibrium. The definition of equilibrium is when there are balanced forces. So we talked about how net force had to equal zero as one condition of equilibrium. Now we're going to add to that, we're going to have the second condition of equilibrium, which says that net torque is equal to zero. When net torque is equal to zero, that means that the sum of the counterclockwise torques minus the sum of the clockwise torques has to equal zero. Just like when we said all the up forces minus all the down forces equal zero, and all the right forces equal all the left forces, like that. That's where we're going with this. Now we're going to talk about torques. The torques that cause rotation counterclockwise have to balance the torques that cause rotation clockwise. If those are balanced with each other, then you have equilibrium. Now this could be used to solve a whole variety of problems. So let's do a few of those. The most basic problem is a seesaw problem. Seesaw problem you may have is a general term for anything you could draw like a seesaw. So you would have a beam, you have your pivot point, and maybe two objects resting on top at different positions. You'll see I labeled my forces. I have force 1, I have force 2, and I have force 3, which is the pivot point pushing upward. So this force won't cause rotation at all because there is no distance between the pivot and that force. So that torque is zero. And we're going to use that to our advantage in later problems. So we need to figure out what that force is. The force of this is equal to weight because there is no acceleration. So I figured out the weight of this one. And then I figured out the weight of this mass. So I got that. This one's pulling clockwise, right? It's going to go pull that way. And this one would pull this way. It doesn't actually pull that way. The torques by each of these have to balance each other so that there's no net torque. But they would, if they did rotate, it would pull in those directions. So you write out net torque clockwise equals net torque counterclockwise, and you can plug in the force, the distance from the pivot. These are right angle forces, so the sign of 90 goes to 1. And when you plug in the numbers, you could find the distance of this, where this has to be placed in order to cause a condition of equilibrium. This force, right, is pulling around in this direction. But if you moved this object closer, so it was less than 0.33, it would reduce the overall torque, causing an imbalance that would cause a rotation that way. This would fall down, this would go up. If you put it at a distance farther than 0.33, let's say at half a meter away, this would then have a greater torque and it would cause rotation around the opposite way. This is another type of problem, very similar, except the pivot is not so obvious. If you look, this is a bridge, so you have pier over here, and you've got another pier here supporting this very straight bridge. And we're assuming there's one car on it, and here's the mass of the bridge itself. The force of gravity acts in the exact center of a uniform beam. So the question is, where is the pivot? Well, you get to choose where to put the pivot. It depends what you're looking for. So the one thing you want to remember about the pivot point is that there's no torque there. So you can put the pivot where there's no, where you have an unknown, and it'll get rid of that variable. So if I wanted to find, let's say, the force of pier 2 that's needed to support this bridge, I could make the pivot point at pier 1. And that would get rid of this torque altogether. And then I'd be left with pier 2, the force from pier 2 pulling this way around this pivot. That's counterclockwise. And these would be pulling in that direction. So force 3, which is the force of the car, would be pulling clockwise. And gravity, the weight of the bridge itself, would be pulling clockwise. So you have the torques from those two items. So if you are given the weight of the bridge, the weight of the car, and their respective, and the length of the bridge and the position of the car, you could find out this force that the second pier has to exert. Depends on what information you're given. Here's another type of problem. This is called a cantilever. So you have a beam, like a bookshelf maybe, with an object on it, and it's just inserted into a teeny pocket in the wall itself. So what happens is, if you think about it, if you put something too heavy on the end of this shelf, the whole thing's going to rotate down around the edge of the shelf there, the edge of the wall. It's going to rotate around that point. The force of the wall above it is really what's holding it in place. So this is the pivot point for a cantilever. It's almost always there, unless you're solving for it. And if you want to know what the force of the wall is on this shelf, how much it has to exert, you need some distances. So I have some distances I wrote on here. Here's the mass of the book, or the object that's sitting on the shelf. Here's the mass of the shelf itself. And so you can, then it becomes just setting up, making sure you put these in the right direction. You have to identify which way is clockwise and which way is counterclockwise, right? This force is pulling down around this pivot point. This one's pulling down clockwise around the pivot point. So you have F2 times its distance, the weight of the shelf times its distance from the pivot, and the weight of the book, right, and its distance from the pivot. And then you can solve for that unknown force. If I wanted to also know the force of this fulcrum, like of the edge of that, what force is being exerted right on this point, I could find that too. So I would have to set up another problem. I could do it two ways. You can set this up again, but move your pivot to any other location. So you could make it this or this or this, whatever you like. Or you could just use net force. So if you go back to the first condition of equilibrium, you can simply add up the forces. So these are all vertical forces. So you'd have F3 minus F2 minus Fg minus F1 is equal to 0. So you could, right, these are your down forces. Here's your up force. Those have to balance each other in order to be at equilibrium. So you could simply find this force 3, which is the force of the edge of at the edge of the wall there, by adding together 646.8 plus 98 plus, what is that, 19.6. And you would get what that force is by adding those together. A more complicated type of problem is a ladder problem. A ladder problem is more complicated because the angles are not 90 degrees, and it makes it a more challenging problem for most people. So here's the ladder leaning against the wall. We're going to assume there's no friction up here, but there is friction holding the ladder in place on the floor. If you don't have enough friction, this whole ladder is going to slide out, translate, right? It's going to slide out that way. So you always have these forces, your friction force, the normal of the ground. You have the weight of the ladder itself, you have the force of the wall. Sometimes someone may be standing on the ladder, or there's a pail on the ladder. There could be objects sitting in different places on the ladder. You once again get to make up where the pivot point is. So you could make the pivot point here would get rid of two unknowns. You could make the pivot point here, that would get rid of this unknown instead. Depends on the information you're given. A very typical problem is to find out what angle, what's the minimum angle you can use before the ladder slides out from under you, which is not a good thing, generally speaking. So to solve it, you do it the same way. You identify your pivot, you identify the forces that you have to deal with and their angles. You need a little bit of geometry here, just like we had to do with inclined planes. And you'll see that if this is the angle you're looking for, this weight force and the friction force make a right triangle. So this angle in here is 90 minus theta. This angle here is an alternate interior angle. This is going to be equal to theta. So this is theta, and this is 90 minus theta. So that's important to identify also. So there's several steps here. One is writing out your torque equation. And then the second part is, once you do that, you need to find, before you could solve for the angle, you need to find the normal of the wall. So finding the normal of the wall means that you first have to find the normal of the ground. the normal of the ground will give you the friction force, and the friction force is going to be equal to this normal of the wall. And I actually ran out of space on this board to show you that step. But let me kind of, if you look over here, right, you would also solve for the first condition of equilibrium on the x-axis, and you would have the force of the wall minus the friction force is equal to 0, right? So you're getting the force of the wall, and that's why the force of the wall is equal to the friction force.